Let's take a moment and go through how to approach and solve a problem such as number 14 in the gas law problem set number 2 done in class Tuesday, August 28th. In the problem we're provided how many grams of PCl5 are placed in an evacuated, which means an empty, 2-liter flask. It's then completely vaporized, which means it's turned completely into gas at this temperature, 252 degrees Celsius. Our first step, let's take the 6.19 gram sample and convert that into moles. Once we have it in terms of moles, we can use the ideal gas law to solve for the pressure in the flask. Using the periodic table, we can find that phosphorus has a mass of 31. There's one atom of phosphorus in our sample, so 1 times 31 gives us 31 grams coming from phosphorus. There's 5 chlorines in our formula, so 5 times 35.5, the mass of chlorine obtained from the periodic table, gives us 177.5. Adding these together will give us the mass of 1 mole of PCl5. Find that 1 mole of PCl5 has a mass of 208.5 grams per 1 mole. Using a proportion where 1 mole of PCl5 is 208.5 grams, we can solve for X, or how many moles are present in our 6.19 gram sample. We find our sample contains 0.0297 moles of PCl5. We can now use Pivnert, the ideal gas law, rearranging to solve for pressure to get our pressure caused by the PCl5 in our 2-liter flask. Solving for the pressure, we find the pressure caused by the PCl5 in our flask is 0.64 atmospheres. In the flask, the PCl5 will now start to undergo a reaction. It's going to form PCl3 and also some chlorine. What we know is that once the reaction is complete, the total pressure in the flask is going to be 1 atmosphere. This will allow us to determine the partial pressures of each of the gases that are present in the flask. Let's use a strategy known as the Rice strategy to give ourselves a framework to solve the problem. The R stands for reaction, the I is initial, the C is the change, and the E is at the end, or when the reaction reaches equilibrium. Earlier we just determined that the amount of PCl5 initially in the flask is 0.64 atmospheres. Before the reaction starts, there's 0 chlorine and also 0 PCl3 present in the flask when the reaction first starts. If we look at the balanced equation, the reaction occurs in a 1:1:1 ratio. We don't know how much PCl5 is reacting, but we do know it's going to go down by some quantity X. If the PCl5 goes down by X, that means the PCl3 has to go up by the quantity X, and the Cl2 has to go up by the quantity X, since the reaction is occurring in a 1:1:1 ratio. We now know that when the reaction is finished, the amount of chlorine present is going to be X from 0 plus X, the amount of PCl3 is going to be X from 0 plus X, and the amount of PCl5 will be 0.64 minus X, and that's what's happening when the reaction occurs. We're also given that the pressure total in the flask is 1 atmosphere when the reaction has reached its final stages. We can use Dalton's law of partial pressures, and that the total of all of the gas's pressures should add up to equal 1 atmosphere. So we add together the quantities 0.64 minus X, which represents the pressure of the PCl5, the quantity X, which represents the pressure of PCl3, and the quantity X, which represents the pressure of chlorine when the reaction has reached completion. Solving for X, we find that X is 0.36 atmospheres. Since the quantity X represents the partial pressure of the Cl2 and also the partial pressure of the PCl3 at the reaction's completion, we now know that both Cl2 and PCl3 each have a partial pressure of 0.36 atmospheres. We also know the partial pressure of the PCl5 is represented by 0.64 minus X. Solving for X, we come up with the partial pressure of PCl5 when the reactions reach completion is 0.28 atmospheres. Doing a quick check of Dalton's law of partial pressures, adding together the partial pressures we have of all the gases in the flask, we get a pressure total of 1 atmosphere, which matches with what the pressure should be in our flask. So check, our work has come out quite well.